Okay, so welcome everyone. I think it's our week 12 lecture, yeah. So we're close to finalize this course. And today we will talk more about computer-aided analysis, and we will dig more into specific methods that are used there for kinematic analysis of planar mechanism. So yeah, so let's start with the recommendations for the remote work, because yeah, now university is closed. So I will put this also in Moodle a bit, but for you to know that firstly, I will ask you to read some chapters from the textbook, and this is Kravish textbook, and I will include the specific chapter in the Moodle for you. Now there will be a pretty simple assignment that will test your understanding of today's lecture. And please note that I will ask you to fill it, to solve it before next week, yeah. And yeah, we'll discuss it. What is this assignment about at the very end? And today there will be, in practice, no coding. Yeah, so because we are preparing only for final assignment, and final assignment will include this kinematic analysis of mechanism. And today we'll talk mostly about the theory of it, because I suppose it's quite new to you. Yeah, so let's see how it will go. Okay. So here are a few slides that you have already seen last week. Yeah. So first of all, about the nomenclature for matrix calculus, and the fact that, let's find like a point area. The fact that matrices are and vector quantities are noted by boldface. Yeah. And with uppercase letters, you have matrices. So usually those are two-dimensional entities, column vectors. This is all column matrices. This is 1D entries, and they are boldface also, but lowercase. Scalars are written as usual, lightface letters, depending on the need. And as we discussed, transposition of A is row vector or row array or row matrix, and 0 is 0 matrix. Next, we talk already about it, that computer-aided analysis is, it allows engineers, in our case, mainly mechanical engineers, simulate behavior of the product before it is prepared. And we use technique called multi-body system dynamics, multi-body mechanical, we will model multi-body mechanical systems. And here you have examples of multi-body systems. So we have some bodies connected with joints, yeah, and they and joints describe the motion that two links, like for example this and this, can have relative to each other. Then we build out of those blocks the whole mechanism, whole kinematic chains, and we assume that it will move in some prescribed motion, and we want to analyze this motion in details. We also talk about method of analysis that usually you have statics, dynamics, and also sometimes we talk about kinematics. Yeah, and we will skip statics. We'll focus mostly about kinematics. Similar methods can be used also for dynamics. If we will have time, we'll discuss it later. Maybe we'll also talk a little about it. Last time we also talked about specific choices of coordinates, and one of those coordinates were Cartesian coordinates. And Cartesian coordinates are chosen in the way that for planar case, yeah, for each body, we select a set of 3 coordinates always, yeah. So it's a no-brainer here. So we assign some position for a point and angle, yeah, of the body. And we do this for all bodies, like in this example, all 3 bodies. So for this 3-body system, we have 9 coordinates. So we have plenty of coordinates here because, as you may remember, it is enough here to use one general coordinate to describe this system fully. However, the advantage here is the description is pretty easy. Yeah, we don't have to, choose some specific set of coordinates, analyze the system topology beforehand. We can just assign those coordinates to bodies and then connect them with joints. So the main advantage of this approach is that it's reasonably easy to write algorithm out of it. So it's nicely designed to make computations using computers. And with those Cartesian coordinates, we have those constraint equations. We discuss about them. They describe the fact that here in points A, B, C, D, we have some joints. And you can see that they follow certain pattern. They are very similar and they are reasonably simple. Yeah. And yeah, so I think this slide is not so needed here. Yeah, so, but maybe we can just tell that for all those coordinate sets that were discussed last week, we can use differential equations of motion. And what is more important here, that for Cartesian coordinates, we have maybe large number of coordinates. However, let's say we assume that we have also modern computers. So the system is just large, yeah, but nonlinearity is low. And what is the most important for us? Derivation of equations of motions is simple, and program development is easy. So that therefore, despite that they might not be as efficient as other choices, yeah, because of easiness of writing programs, we'll choose them for our further work. Simple note about general purpose program. And this was at least partially also discussed for previous from in previous parts when we discussed, for example, if we should implement, let's say, integration procedure in generic manner or in specific manner. Yeah. So for general purpose program, the idea is similar, that we have we provide some data from the user. Yeah. For integration, it was in a function that should be integrated and for example, interval, number of points, etc., or tolerance. And here for mechanisms, we must find a way somehow to define the mechanism. So describe the bodies, describe joints, initial position, what are forces that act on the system or similar manner, and what is, for example, the time domain of the solution that we want to get. This is input, and it's also called preprocessing. Middle part is just to automatically generate equations of motion without, human now intervenes. So this is the task, automatic task that should be done by computer, and then computer should solve those equations. And at the very end, there is post-processing or output phase that we want to provide results to the user. And to get it reasonably easy, we choose this multi-body system method for analyzing mechanical bodies. And we choose Cartesian coordinates because it's reasonably easy to generate equations. And this is the most demanding part in our development, how to generate those equations, because solution is similar in each case. Post-processing is also very easy for Cartesian coordinates. Okay, and now a little about practicalities. Yeah, so we start from the scratch. So about vector representation, because we have a lot of vectors. Okay, so from mathematics and classical physics, we usually know geometric vector. Yeah, so, and it's denoted with the arrow about the quantity. So A with arrow, so this is a vector. It's a geometric vector. And we know that it begins at some point A and ends at some point B. And this is the full description. We can just simply draw it on the plane or on the space. It has some properties like magnitude, yeah, and direction with some unit vector. Zero or null vector has no magnitude, yeah, because A is zero, and we can define some basic operations on those vectors, yeah. Like addition and linear combination. There are also another properties of those vectors or operations like dot product, yeah, that is denoted with dot, as name suggests, yeah. So a dot b vector, it's scalar, yeah. So here we have just scalar number, so it's equal to magnitude of a multiplied by magnitude of b multiplied by cosine of the angle between those two vectors. Here is the equation when we use coordinates, and we can see that dot product is commutative. One of the things that are important for us, the dot product is zero, so it's equal to scalar zero when vectors are orthogonal, when they are perpendicular to each other, because cosine of pi half, for example, is equal to zero. Also, dot product of vector times vector is equal to a magnitude square, and it also came directly from the definition. And here is how it looks visual when we visualize it. Yeah, two vectors and angle between them. And here is also written that that dot product can be used as scalar projection. Yeah. Yeah. Okay. Another common operation for product for vectors is cross product. Yeah, and result of cross products is vector, like here. Yeah, so here's magnitude of the vector that is equal to magnitude of two vectors AB and sign between those vectors. And here is U. So this is direction of the vector. And as you may remember, U is perpendicular to the plane created by vectors A and B. Here are some numbers. So firstly, let's go note that it's not commutative, but so the cross product of B vector times A vector is equal to minus A times B. And how to define U? It's defined by using so-called right hand rule. Yeah. So for example, if you have a right hand, yeah, if your index finger is along A and middle finger is along B, then your thumb in perpendicular direction to those two tell you what is the direction of the cross product. Okay, so that was about geometric vector and basic operations on it. And geometric vectors are not so great for example computers. They're great for some geometric methods. So for visualization, you know, to draw them or to, you know, manage them graphically. But for computers, we need numbers. Yeah. So how to change a geometric vector to algebraic vector? We must put him into some reference frame and then find their components. Yeah, and it's shown here on the figure. Yeah, that if we have vector A, and this vector is put into the reference X, Y, and Z, and with unit vectors A, J, and K, yeah, we can easily find the coordinates or components of this vector AX, AY, and AZ. And if you put those coordinates in common vector, then we have representation, algebraic representation of the vector. Note also that, for example, AX is equal to a scalar product of A vector A times I, the times unit vector I, and so and so. So yeah, so it can be uniquely defined as that, and now we can use it for our computations. However, of course, if we choose to use different reference frame, those numbers will be different. They describe exactly the same number. Of course, the magnitude is the same, but the numbers change because the numbers are meaningful only with respect to provided reference frame. And now with this, with algebraic vectors, we can also define similar operations. Dot product is simply multiplication of those two vectors. So first is converted to row vector, and this is standard column vector. So dot vector of A and B is A transpose times B, or because it's commutative, B transpose times A. And if we will write it explicitly, it's simply the sum of the products of their components. To define cross product is a little more demanding because the result is also another vector. So first we must define a skew symmetric matrix. A skew symmetric matrix, it means that transposition of this matrix is equal to negative of it. So if we have vector A with components A1, A2, and A3, yeah, we can define a skew symmetric matrix associated with it, and it's described here. And with that definition of the skew symmetric matrix denoted with type, yeah, we can write a cross product. So cross products of A times B, A and B is equal simply to skew symmetric form, this A tilde of the first vector times second vector. Yeah. And here is the explicit form of it. Okay, and any questions for that part? Okay, great. We of course will use those vectors quite intensively in our derivations for multi-body method. But here, let's introduce some basic concepts for multi-body method. So first thing is rigid body. So this is some part of mechanism that do not change in shape during the motion. Yeah, so we just simply assume that our mechanism is stiff enough that any changes in their shape, because in reality there's always some deformation, is small enough that we can assume that it doesn't deform. It of course makes analysis far easier, because in theory for rigid body we need in planar case only 3 coordinates, and for deformation body we need infinite amount of coordinates. And we'll consider only rigid bodies, and this is valid for many practical applications. Kinematic pair, also called as a joint, is combination of two links, yeah, in contact, and imposes constraints on their relative motion. We will describe it shortly. Degrees of freedom, so this is number of independent quantities that describe system location, yeah. And so, for example, if we have general coordinates, also the number of degrees of freedom is equal to the number of general coordinates. And kinematic chain is assembly of rigid bodies connected by joints. In our case, only rigid bodies. Yeah. So for those mechanisms that you have already seen, yeah. Let's use some pen. Yeah. So rigid body, yeah. So all those elements that have names here are rigid bodies, yeah. So for the first mechanism for pendulum, we have only one rigid body. Here we have 3 rigid bodies, and similar from this for this mechanism, we also have 3 rigid bodies, yeah. Kinematic pairs or joints, yeah. For pendulum, we have 1 joint. It's here, yeah. For this 4-bar mechanism, we have 4 joints. All those dots here. So we have 4 joints, and as you can see, they restrict the motion between 2 bodies, or body and the ground. And here, for the slider crank, we have 4 joints, and 4 joint is here. Yeah, so that motion that we have, that we restrict the motion of this 4th link only along this axis, it also describes translational joint. Number of degrees of freedom. Yeah, so in our simple case, numbers of degrees of freedom is ever equal to 1. So this pendulum can only rotate in this direction in planar, so it has 1 degree of freedom. So 1 generalized coordinate is enough. We discussed already about this 4-bar mechanism. It also have 1 degree of freedom, and same apply here. Yeah, it has also 1 degree of freedom. And kinematic chain is of course it's of course this the whole mechanism is kinematic chain. So this is the whole kinematic chain here similar. So the full mechanism is simply this assembly of this full mechanism that contains all the bodies and all the joints. It's a kinematic chain, full kinematic chain. Okay. Any questions about that part? If not, then we can continue. Cartesian coordinates. So we choose to use Cartesian coordinates because we believe that it will be easy to describe the motion of the system. Okay, and it's done in the way that each body I has body fixed xi coordinate system, like here. Body location is given in global coordinate, like that. Yeah. So we can easily describe the location of the system. And we need third coordinate in planar case to describe rotation of the body reference frame with respect to global frame PO or XOYO. Yeah. And one of the common tasks that we have to face is how to describe the point S in all those coordinates. And please note that in general, position vectors are 3 vectors that we have seen on the example of coordinates, because this is everything is done in spatial case. However, in planar motion, and we will deal with only with planar motion, we will treat them as 2 vectors. So they will have only 2 components. That's why here position vector has only 2 components. So now we have to somehow define how to move from one reference frame to another, because yeah. And it's done with transformation matrix, rotational transformation matrix. So here we have S vector. So this is the position of point S with respect to this bar denote that this is respect with this is described using local components. Yeah. Because all those s's, yeah, no matter if this is s with bar or without bar, describe the same vector s, yeah. But with s bar, we describe this vector s with respect to local coordinate frame, like here p1, yeah. And without bar, we describe it in global coordinates. And the story here is that s with bar is constant over time, because this body is rigid. We have this frame P1 or PI attached to this body rigidly also. So under these conditions, the coordinates of that vector are known, and they are always constant. However, we must describe the position, that point and that vector in global coordinates. And the main reason for that we have multiple points, multiple bodies, and multiple local coordinate frames. But the final equations, kinematic equations of motion, will be written with respect to global coordinate. So we have to find a way to transform all our local entities, like this vector S, to global coordinate, because at the end, we must write everything in single coordinate frame, and this will be our inertial global reference frame. So how to describe point S in global coordinates? So like here, yeah. So RS, so the position of the vector RS, so position of vector S in global coordinate is equal to those two vectors, those two blue vectors. So this is the position of a local reference frame plus vector s, but described in global coordinates. So how this is reasonable and easy. And of course, this is in local. We must define it in global coordinates, and we transform it from local to global coordinate using so-called rotational transformation matrix of body I. And it's defined as here, yeah. So phi is angle between global and local coordinates. And with this angle, we can define this transformation matrix as cosine phi minus sine phi, cosine phi. Yeah. So explicitly writing, we can explicitly write it in that form. And here we have this notation with bar denotes quantities with local components, and we can transform using matrix A from local to global. And please note also that this matrix, first of all, this transformation is unique. So we can also define inverse transformation. And this matrix is orthogonal. And thanks to this, we can transform we can define transform inversion simply by transposing this transformation matrix. So if you want to go from global coordinates to local coordinates, we simply use a matrix by transpose. Okay, so here's a simple example with some numbers and some mechanisms. So yeah, so we want to describe point B that is located on body 3. So this is local coordinate. Instead of using x with numbers, it uses c and eta to describe x and y axis, local y axis. Yeah, and we have defined some numbers here. That first of all, location of this reference frame. So vector R3 has coordinates 1.2 and 2.5, and the angle between global and local shown here, yeah, phi 2, phi 3 is equal to 0.4, 5.67 radians, for example, yeah, why not? And body point B on this body has, of course, a constant local coordinates, and they are defined like here, yeah, so local coordinate x, it would be like here, yeah. So it would equal to minus 1.8, and local coordinate y, like here, or like here. So this is on that axis is 1.3. And there are two questions. What are global components of vector SB? Yeah. So what are global components, and what are global coordinates of point B? Okay. So an answer for it is that we just need to perform the transformation that was shown in previous slide. So global components of vector S can be defined like that. That global components of point S, yeah, that point to point B in the reference tree is equal to transformation matrix from global coordinates to coordinates in reference 3 times local components of this vector, because they are given here, yeah. And of course, transformation matrix has always the same forms. So this is cosine phi 3 minus sine phi 3, sine phi 3, and cosine phi 3. And we multiply it by vector S bar. And of course, S bar has components minus 1.8 and 1.3. Yeah, they're taken from here. And after substituting numbers here, we get something like that. So in our global coordinate, yeah, this vector has some small negative value, minus 0.72, yeah, and larger one positive y positive value 2.1. And so this is the way to describe that vector, yeah, so that part in global coordinate. Now, global coordinates of B. So we are looking for coordinates of point B only. Yeah. So from point B, we must add two vectors. So we must add vector R3 and S3, but described with respect to global coordinate because we must be consistent if you want to get any reasonable result. So R3 was provided here. Yeah. And this is those and that second part. So S3 with respect to global coordinate was already computed. Like here, we just must add those two, and we get those numbers. Any questions for that, or is it clear?
I'm clear.
Okay, great to hear it. Now, kinematic constraints. So this is another needed part. So we tell how to describe bodies. We need coordinates, yeah. And we describe how to transform some kinematic properties, position vectors from one body to another, or from body to global coordinate frame. And now about kinematic constraints or joints. Yeah, so bodies are interconnected bar joints, yeah, as we discussed. Yeah, and we must define them, define them, and find a way to describe them. So for this mechanism, it's called quick return mechanism. Yeah, it consists of 5 moving bodies shown, and they are denoted with numbers like 1, 2, 3, 4, and 5. Yeah, and here is more. This is one way to describe it, and this is another way. Yeah, depending what do you prefer. Both those descriptions are equivalent. And now what do we have here? We have 5 revolute joints, A, B, C, D, and O. Yeah. So all those revolute joints, yeah, are here. Yeah. One here, 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 and they are usually denoted with circles. Yeah. So we have those 5 revolute joints and 2 translational joints, T1 and T2, because this box here describes that body 2 can move with respect to body 3 only in the direction with respect to that body. Yeah, and similar here, this box tells us that body 5 can move with respect to ground only in this direction, left or right. Yeah, and we state that kinematic joints in that system and any other system can be described as algebraic constraint. So we can write simply some algebraic equations to describe those constraints. And thanks to that, yeah, we will define the system and we will be able to analyze it. So firstly, we'll talk about revolute joints. So in planar case, if we have revolute joint between body I and body J at point P, it means that that point is constant with respect to all those bodies, and with respect to this point, both bodies can just rotate. This is the common axis of rotation. And how to describe that joint? So firstly, we observe that point P can be described with respect to both bodies. So we have 2 coincident points. Point PI described with respect to body I, and point PJ that is described with respect to body J. And from that, we can write loop equation. Yeah. So we can describe that sum of this vector plus this vector plus this vector and this vector gives us 0. Yeah. So here it is written by, okay, I will change it to pointer. Yeah, so here it is written using geometric vectors. Yeah, so Ri plus Si minus Sj minus Rj is equal to 0. And here it's written using algebraic vectors. So our constraint equation, and please note that we will note constraint equations using capital C, is like that. Here we use those transformation matrices because we want to describe those constraints using body coordinates. Yeah. So vector Ri contains two body coordinates because it tells us where is the local coordinate frame. And also transformation matrix contains coordinate because it depends on the angle between local and global coordinate frame. And with this description, S is constant, so it has no coordinates. Okay. So this is simply a rewritten version of this vector, and it uses coordinates of the bodies, the Cartesian coordinates of the bodies. Simple, simple. And so about revolve joint, here you can see how it looks when we expand it. Yeah. So after expansion, yeah, so we multiply all those transformation vectors, so cosines and sines phi I and phi j times those constant entities of vectors S. And here we can clearly see those coordinates. So here is xi, yi, and phi I, here, and here, which are coordinates of the I body. Those values are constant. Here are coordinates of body J, those one, and those values are also constant. So this is very convenient way. Another thing is because revolve joints form in planar case two constraint equations, so it means that it reduces the whole system, the number of degrees of freedom by 2. So here we have two bodies, and that system of two bodies connected with one revolve joint has 2 degrees of freedom, because free body in planar case has 3 degrees of freedom, 2 translations and 1 rotation. We have two bodies, so 6 degrees of freedom minus 2 constraints, or 1 constraint with 2 equations. In total, we have 4 degrees of freedom. Translational joint, okay? And it means that those bodies can slide but not rotate with respect to each other. Yeah. So with respect to body I, body J can move only in this direction. But of course, in opposite, it works the same in opposite way. So with respect to body J, body I can only translate in this along this axis. Yeah. And one of the way to define translational joint is to find 3 points on the common axis of translation. Yeah, so this is axis of translation. We have here 3 points, QI, PI, and PJ. Yeah, and QI, PI are written with respect to one body, and PJ is written with respect to second body. And having those points, we can define the first equation. Yeah, that equation that says that all those points are always in line. And this is defined like that, yeah. And you can find those entities here. So Ni is vector that is perpendicular to this axis of translation, and D is vector along this axis. And here we write this cross product, because if this is perpendicular, not cross product, sorry, dot product. If those are perpendicular, we know from the definition of the dot product that it must be equal to 0. So we're required in practice by writing here that that vector and that vector are always equal to 0. And how to find the n vector? Simply, if we define S vector using points Qi and Pi, we find a perpendicular vector by switching the components and putting minus on one of it. It doesn't matter on which, it is just important that this is perpendicular. Second equation tells us that those bodies cannot rotate with respect to each other. And it's stated here. It states simply that the relative angle between all those bodies is constant. And this is taken just from initial values, because it doesn't have to be at initial 0, but it says simply that they can rotate as a whole, yeah? But always this angle of rotation is equal to 0. So they must just rotate together. And in the same way, like for revolute joint, for translational joint, we have two constraint equations. So it means that we reduce the number of system degrees of freedom also by 2. Yeah, so here's a simple example that describes how to find important point for our joints. Yeah, so we have here 3-body system, at least, the part of the system that consists of 3 bodies, body number 2, body number 3, and body number 4. And we have here 2 joints. So one is translational joint between body 2 and body 3, and another is revolute joint between body 3 and 4. So to find information about revolute joint, we need just position of point A. Yeah, and it would be perfect to have this position with respect to body 3 and body 4, and that's why here we provide 4 values. So here are coordinates of point A with respect to reference frame, local reference frame 3, and here are some numbers, and here is the same for body 4. So we provide coordinates of that point with respect to that body. Okay. And this is enough for us to write constraint equations for revolute joint, like here, because here we have xi and yi, as well as xj and yj, and all other entities depend on system coordinates. So we can easily write these equations. For translational joint, we need, for example, 3 points, so we can define points on a common axis, that is axis of translation B, C, and E, for example, here, while BC is described in one body, and E is in the second body. Yeah, and same story. We must find the coordinates of those points in certain reference frames, local reference frames. So we write the coordinates of point B in second coordinate frame, 0, 0, defined here because why not? Second point C, similar, 1, perfect number, and some other point also on this axis, and it's defined with respect to what? To second body, so with body 3. And having that, we can simply write that equation, because that part depend on those coordinates, yeah, and those coordinates depend, depends on those 2 points, and D is from 1 point on one body and second bond on second body, so it's point from here to here. So it also depends on those coordinates plus coordinates of the bodies. So with that, with help of that, we can easily write our constraint equations. Another reasonably useful set of constraints or joints are so-called simple constraints, and we describe the simple constraints usually with respect to ground. So when one body is non-moving, and because here we can tell, for example, for that translation of slider 3, with respect to global coordinates, that for that motion, x3, is always constant. Also, angle for that body is always constant, and only y is changing. And as you can imagine, it's reasonably easy to write equations in the form that x3 is constant or phi3 is constant. Similar apply to that slider. Simply here we have defined that y coordinate in this motion is always constant with respect to body form. Also rotation. Okay, it's not with respect to body force. It's location y of that coordinate frame is always constant. Also, angle of rotation of this body is always constant because as it moved like here, it cannot rotate in one or another direction. Similar thing we can define for revolve joint here, because here we know that x and y, are constant or not. No, they are not. Sorry about it. It depends how we define local coordinate frame. Because if we will define local coordinate frame here, like standard, so we define it with respect to center of mass. If center of mass is here, then no, those coordinates are not constant. We only if we would like to define coordinate frame here in that exact point that it will work. I hope it's clear. So how to define those simple constraints? Like here, because we define that they are always constant. So we must find that the value of this constant from initial assembly, and we just say that coordinate minus its initial value is always equal to 0, and that's all. So C1, 2, and 3 are some constant quantities, and because all those constraint equations are scalar equations, so they remove just 1 degree of freedom from the system. And here is how they look in practice. So by constraining x, this body can move up and down and rotate. By constraining y, that body can also move here left and right and also can rotate. And by constraining angle, body can move in x and y, but it cannot rotate in any of the directions, so it must preserve its orientation for the whole simulation time. And okay, and the last main topic that is connected with constraints are so-called driving bodies. So if we and this is for the need of kinematic analysis, because in kinematic analysis we do not care about forces, but we have to somehow induce motion. So the common way to introduce the motion is, for example, to say that that link is so-called driving link, and it's rotate with constant angular velocity omega. You have seen this example. I think it was also a part of the assignment. So this is so-called driving bodies because its motion depends on some quantities explicitly on time. And if we will use the same form as simple constraints, this is the simplest way because we can use a different form, but this is just this is a very simple way to describe it. Then we can enforce that the motion of our coordinate x, y, or phi directly depend on time. And for example, we can, here in this example, we can write that angle of rotation of this link I, driving link I, has some form of function of time and can take this form. So it has some initial value taken from initial coordinates, initial assembly, plus omega times t. And that's all. And if we will enforce this constraint, we'll ensure that that link rotates with constant angular velocity omega. Make sense? I hope this makes sense. And now, if we will define all our bodies, we'll define all our Cartesian coordinates. We'll gather together all our constraint equations due to joints, like revolute joints, simple joints, translational joints, and we'll add to this our driving joints. And we'll do this in the way that all those joints will describe the motion of the system completely. We can perform kinematic analysis. So if we gather all our constraints into vector C and all our coordinates, Cartesian coordinates into vector Q, we can tell that N is the number of coordinates described with the configuration. Yeah. So like here, we have 3 bodies. So the size of Q is equal to 9, because for Cartesian coordinates, all of those bodies will be described with 3 coordinates. Not this direction, sorry. M is number of kinematic constraints. So this is the size of vector C. Like here, yeah, we have 1, 2, 3 revolute joints here and 1 translational joint. And yeah, we can also use here simple joints, but let's say that we use revolute and translational joints. And in that case, it means that we have 1, 2, 3. We have in total 4 joints. All of those joints has 2 components, 2 equations. So in total, we have 8 equations. So for that system, size of C is equal to 8. So M is equal to 8. So in the simplest case, common for planar, if we will subtract N and M, we'll get the number of system degrees of freedom. So like here, our result is equal to 1. So we already thought that this slider crank mechanism has 1 degree of freedom. We now can prove it even with those equations when we define the number of constraints and we compare number of constraints and number of coordinates. So to fully describe this system, we need one extra equation. Yeah, and to describe so we need those k driving constraints to solve the system. Yeah. And like here, we can use this equation. Yeah, that the angle of this link, we call it driving link, is described with that function that is explicit on time. And by defining the number of constraints equal to number of coordinates, we can solve kinematic analysis. So we can find Q for all given times t equal to ti. If you solve the assignments, you have already performed a position analysis. There was also a question about velocity analysis. It was also quite simple, and you can also perform acceleration analysis. So as you notice, if we gather all the constraints into vector C, we can solve using, for example, Newton-Raphson method, equation C equal to 0. And we can solve it for different values of t. Yeah. And then we get out of this equation, we'll get out of this equation, we can get Q1, yeah, Q2 up to Qn, and for respectively T1, T2, Tn. Yeah. So we need to solve nonlinear equations using Newton-Raphson method for all those coordinates n times. If we have n time, and if we have n time points. Next, there is velocity analysis. Yeah, and if you will take a look directly, you can notice that velocity analysis doesn't require solution of nonlinear equations because this is linear problem. And simply, this is our Jacobian matrix times velocities is equal to something. This something is equal to minus a constraint equation with respect to time explicitly. For acceleration analysis, we have quite few extra terms. They look quite terrible, but you don't have to bother too much about them. There are another ways. I think that far more pleasant to calculate those entries, and we'll discuss about this next time. Position vector derivatives. This is another important topic because if you want to get all those derivatives, velocity acceleration analysis, we also must know how to compute derivatives of our position vector in this form. So we already talk about this, and we know that here we have, of course, coordinates directly, yeah, and here we have coordinates, and this is constant. So first time derivative. So velocity of point S with respect to global coordinate frame is equal to velocity of that frame times relative motion with respect to that frame. Yeah, it is known from mechanics, classical mechanics as well. For sure, you know how it works. So so this is of course direct derivation because it contains simply our coordinate. So simply it's r dot. And for that, it contains cosine signs. We can write it explicitly as that term. It's constant matrix omega times our transformation matrix. This is constant vector. And of course, we have internal coordinate, derivation of internal coordinates. So we have here phi I prime. Yeah. And you can check that if you would differentiate this transformation matrix, you will simply get omega, which is this matrix 0, minus 1, 1, 0 times this A. Okay. So this is first derivative, reasonably simple. Second derivative, follow the same scheme. Yeah. So the second derivative we will base on that equation. So of course here we can directly differentiate it. Second term is differentiation of this, also directly. So this part is the same, and this is second derivative of angle phi I. Here we have minus, because if you multiply omega times omega, because here we just differentiate second time this matrix, a transformation, rotational transformation matrix, omega times omega is equal to minus at the identity matrix. So we have minus I. And of course, we get this internal derivative once again. So phi dot I is squared. By the way, in classical mechanics, you will get the same solution. Yeah. Okay. And in practice, that's all for today. Yeah. So today we discussed about many important basic topics. So there was no programming. Yeah. We discussed about how to define the coordinates for the body. And by defining coordinates by the body, we can easily define the coordinates for all the bodies in the system, so the coordinates of the whole system. Then we talk how to write some quantities in global coordinate frame, having them in local coordinate frame, because it's easier to get properties in local coordinate frames, but at the end, we always must go to the common frame, and this is the global coordinate frame. And yeah, this is by using this transformation from local to global. Then we discuss about the joints. So the most common joints like rotational joint, translational joint, and simple joint, and how to define them, how to write them. Then we talk about kinematic analysis. that it means that if we define the system and all their coordinates, and we will add those algebraic constraint equation to the system together, we can perform position, velocity, and acceleration analysis. We must describe the motion explicitly on time, and then we get the solution for all our coordinates. So we cover all those basics, including those vector derivations. And on the next week, we'll discuss how to put it together into working program. And before that, there is assignment for you. You will get all this, of course, in the Moodle, including the textbook that will contain all those problems. And those problems are to challenge your knowledge about, it's about to test your understanding of the system, transformation, coordinate, and so forth, because before we'll get to the real programming, it's good to understand the basics. And because all those problems are in the form of consideration, you will consider the different mechanism, coordinates, and how to transform from one to another. What are so this will be extension of what we have discussed, of course. So it's nothing about programming. So that's why I ask you to submit, of course, PDF with solutions, but it can be scan of your handwork. So you can just take pen and pencil, and I think this is the best way, and solve all those tasks there, and then scan them and upload them. But please, of course, take care about quality of your solution, that this is everything readable and clear enough. So don't go to the corner of your room and take photos in different angles. Just, please make it readable, that I can easily read it and have no doubt about how it looks like. And of course, deadline is for the next week, so just before our next lecture. So that's all for today. Do you have any questions? It looks like no, so I will stop recording.